Dear colleagues, by means of this tutorial we will learn how to size a cooling circuit or a heating circuit where a defined volume is taking place. This has a lot of applications both for refrigeration and for heating, every time when we have to do with a buffer tank. And the question we need to answer is how much time is required for increasing the temperature of the tank from status A to status B or decreasing. And what is this time depending upon? We start with the theory and then we see a couple of applications as usual. I hope you will enjoy it. The problem is non-stationary. It does mean the status of the system is continuously changing with the time. Let's start with the cooling case, then it's also valid for the heating case. We have one closed loop around the tank and we want to cool down. The loop consists of one pump, the heat exchanger, and since the loop is closed, the pipe is leaving and returning to the same tank. We call this one the process loop. On the other side, we have the cooling medium, also another pump, and the heat exchanger in common. And because this process fluid is getting cooled, the service fluid is getting heated. And there will be another cooling system here to bring that fluid in the same conditions. But we won't take care of it now. Here is represented a schematic of the system. The tank is having a constant volume and a temperature which changes with the time. We assume the flow of the process pump and the flow of the service pump are constant. Moreover, we assume the incoming temperature of the service fluid T1 is constant. The heat exchanger is defined by its geometrical property, the heat transfer area A and the heat transfer coefficient K. Altogether, we consider the product Ka as a constant during the cooling process. What is changing? Apart from the temperature of the tank T, the delta T across the heat exchanger on the left side and the delta T on the right side. Totally, we have three variables plus the heat exchanged, also four unknowns. To solve the problem, we need four equations. The equations we write are two coming from the energy conservation and two from the heat transfer laws. The energy conservation says the heat lost by primary fluid is gained by the secondary one. And we can express the heat lost or gained in the same way. It is a product of three terms: the specific heat C, the flow rate Q, and the delta T. For the service fluid, we write the same variables with the subscript 1. Combining them, we get a relationship between the two delta T's. The first heat transfer law says how the heat is transferred across the heat exchanger, and this is our equation number 3. We have still a product of three terms. One is the surface area and the heat transfer coefficient K of the heat exchanger, and then we have a delta T, the mean delta T, which is the delta across a section of a heat exchanger. Actually, this delta changes between the entry and leaving section, as represented here in the chart. So we take an average. The pure theory says that we should use a logarithmic average, but to make it simple, we take the arithmetic instead, and this does not change significantly. The fourth and last equation says how the tank is changing its temperature with the time. This is the only equation with the time. Combining now the first and third equation, we get an expression among t and delta t. If we call delta t as the variable x and the ratio displayed here as r, which is a constant, we can get x from the second equation, and by plugging it into the first, we find a relation where only the temperature appears. And this is a differential equation of the first order, linear, where the temperature appears as a function of time. To solve this equation, we need to make some developments. First, we bring t on the left side and t1, which is a constant, on the right side. Then we introduce the constant alpha, so defined, and the alpha dimension is time to minus 1. So 1 over alpha is a time.
Because T1 is a constant, we may write T1 also within the differential sign, and we bring the difference T minus T1 at the denominator. Thus, we can integrate both sides of the equation and we can solve for the time. This is the solution. Practically, the function t is an exponential negative function having an asymptote for the temperature T1. Let's do a numerical example. We want to cool down a tank of 10 cubic meters and the fluid is a mixture of water, so the heat capacity is known, C, and knowns are also the starting temperature and target temperature, respectively 70 and 50 degrees. And also we have at disposal a pure water, so its heat capacity C1 is also known, and the supply temperature is 25 degrees. Moreover, we know the flow rates Q and Q1 and the heat exchanger parameters K and A as a product together. Our target is to find the cooling time. We need to calculate the parameter R and alpha, or 1 over alpha. R is given by this expression, therefore 1.20 dimensionless. And by means of R, we can calculate the constant 1 over alpha, and we find 1533 seconds. Finally, the cooling time is a product of that value times the logarithm of the ratio between T0 and T1, so 70 minus 25, and Tf minus T1, 50 minus 25. That is 900 seconds, 15 minutes. And here we have a nice chart. Another example, this time for a heating process. We can use the same formula. Let's assume the same parameters as before, apart from the temperatures. Here we have a starting temperature of 50 degrees. We need to get 70, and we have at disposal a service fluid at 75 degrees. By plugging the new values inside, we remember that for R and alpha the values are the same. We get now 41 minutes. The reason why the heating process is longer stays in the temperature of the service fluid, which is just 5 degrees higher than the target one. And here also a chart.
This tool can be used to solve the problem of heating or cooling when the system is closed, when there is no mass exchange across the boundaries. In this example, we have seen a liquid which is changing temperature. It cannot be used for a vapor or when any latent heat is taking place. For those applications, we need to develop another model. I hope you have enjoyed it. Therefore, see you again.